we're gonna move on to we're gonna go backwards a little bit, but still be a little bit on 6.4. 6.2 has to do with right triangles. 6.4, a section of 6.4, has right triangles, but specifically only about finding the angles in the triangle. 6.2 is just about finding the sides, but I rather just put those two ideas together. Now, since we are dealing with right triangles, once again, we can look at our trig ratios, right? I've repeated these multiple times, right? We have our, what's it called? Our mnemonic, SOHCAHTOA, right? That helps us. Sine is opposite of hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. And always remember, sine corresponds to cosecant, cosine corresponds to secant, and of course tangent corresponds to cotangent. And since we're dealing with right triangles, something to remember is a right triangle has a 90-degree angle. There's also the Pythagorean theorem, Pythagoras theorem, that tells us that the sum of the two legs squared is equal to the hypotenuse squared. And because we are going to be solving right triangles, meaning trying to find every missing angle inside, we also have to remember that the sum of, and this goes for any triangle, not just right triangles, but the sum of the interior angles is 180 degrees. Now, to make a quick note, because sometimes that idea of opposite and adjacent gets mixed up a little bit. So let me zoom in here. Now, if I'm discussing this red angle, when I say opposite, I am talking about the side that is subtended by the angle. So this is the angle that's being created by that red theta. And this is the side that's captured by it. That's what subtended means. That's why this represents opposite. Now, the side that's right next to this angle is immediately here on the bottom. So this is the adjacent side, right? This will always be the hypotenuse. So that doesn't make a difference. Now, the difference does come when we look at the opposite, let's say the blue angle. Opposite of that angle is going to be on this side. And why would we switch it up? And you'll see in some examples that sometimes we'll need to use a opposite angle to use, not always the bottom corner. And again, a right triangle doesn't always have to be pointing in this direction or have this orientation, right? Sometimes it might be written like if it's pointing down, or it could be slanted, right? There's many variations of placing a right triangle, right? I can always rotate it. So just to give you guys an idea, right? A right triangle can rotate, and it's always a right triangle, and the opposite is always the opposite, adjacent always adjacent, depending, of course, on the angle you're looking at. Now, here, this side becomes the adjacent side for theta, the blue theta. So just keep that in mind when you're finding your opposite over your hypotenuse, just because depending on the angle that you're looking or using, the opposite, of course, is going to change. So just something to keep in mind. But let's just jump in, do some examples. All right, so dealing with right triangles, hence the emoji, this sort of ruler. Forgot what you call this ruler. In construction, there's something similar to this. It's known as a speed square that can help you find angles, pitches on roofs, help you make right angles, different things. But I think there's a specific name for this one, but I forget. But in construction, there's something like this. It's known as the speed square, if anybody uses them. But let's just jump right into an example here. I'll do a couple and then I'll give you guys an assignment. And I'll try to show you. I'll try to specify like which part is how 6.2 is going to be and which part's going to be like 6.4. So this first example, I'm just going to draw it normal. In the book it might be oriented differently, but still a right triangle. That's this little box, right, implies that 90-degree angle. And then here's our given information. So we have 40 degrees. And then we have that this side is 2. And our missing, that's our missing angle. There's our missing side. And our hypotenuse is missing as well. Now, there's a couple ways to solve this triangle, right? For example, I know this one's 90, this is 40, and that means I know the sum of these interior angles has to be 180. So if you want, you can just set this equal to 50. But I'm not going to do that because that's not always going to be the case. Now, if you do have that situation where all you need to do is add the interior angles, so 90 plus 40 is 130. So to get to 180, all we need is 50. But I'm going to find this angle using our trig ratios, just so we can have practice. Now, if I had one more side, I would also use my Pythagorean theorem to find all the missing sides. But once again, I want to use my trig ratios to find these answers. So I'm not going to use the sum of interior angles. I'm not going to use the Pythagorean theorem. I'm going to do this all by using trig ratios. Now, one rule of thumb, and this is what I use for the next couple sections, is going to be the same concept. And that is, whenever you're trying to find a missing variable, the number of unknown variables you have should equate to the number of equations you're introduced to or can find. What do I mean by that? If there's one unknown variable, one equation will suffice to help you solve for that variable. If there's two unknown variables, then you'll need two equations. I don't know if anyone remembers how systems of equations work. That's usually when you were involved with multiple variables missing. Hence, we needed multiple equations to solve for those variables. Now, so what does that mean? What trig ratio do I use? And there are techniques and strategies to know which is the best trig ratio to use, but I truly just go with pick one, right? Like just randomly pick one. As long as you remember the rule of thumb that you only want to have one unknown variable in your equation, so because I don't want to need a second equation to help me solve. That's what I'll do. So for example, to start, I'm just going to start with sine. And I'm going to do sine of A. So that's this angle, right? That's my argument. And I know sine is equal to opposite. That's going to be 2 over adjacent, which is B. And this is exactly what I don't want. I don't know this angle and I don't know this side. I would need a second equation to be able to solve for these angles. So I don't want to take this route, right? And that's it. That took a couple seconds. I didn't want to use it. Now, let's take a different route. Maybe you want to use a different trig ratio. Let's say, well, for example, I didn't know this angle. Maybe for the next one, I'll use angle 40. And let's just choose a random trig ratio. Let's go with tangent 40 degrees. And that's going to be equal to, remember, tangent is equal to opposite, which is my angle, my side B, over adjacent, which is 2. Because for 40, remember we just said here, if this is the angle above, opposite is the one across from it, adjacent is the one next to it. So we have, let me move this actually over here to be able to work with it a little better. I'll put it here. Now, this is where we need to use a little bit of algebra with equations, and all I'm gonna do is multiply, because my goal now, there's only one unknown. I have one equation. That's enough for me to solve. So I'm gonna multiply 2 to both sides to help me isolate my variable. And that means I have angle side B, is equal to 2 times tangent 40 degrees. Now I did say at one point we will need our calculators. And this is a perfect example because I don't know. I know tangent of 45 degrees, tangent of 30, 60, 90, 120, and so on. But I don't know tangent of 40 degrees. This is where I would need to take a calculator. And of course, it's going to be an approximation. So the approximation is going to be 2 times, and luckily I can pull up my calculator right next to my problem. Now, something you have to be careful, of course, this is probably not your traditional calculator, but if you look at this button, I know it's hard to see what I'm pressing, but hopefully some of you can see it. It's right in this direction where it changes from rad to degree. Now I want to make sure this option is in degree. This is going to be different for depending what calculator you're using. Sometimes you have to go to mode, you have to go to sometimes yours has the direct button. For degree and radian, you have to find that option somewhere in your calculator, and if you can't find it, message me on Pronto, and then you can send me a picture of your calculator and we can find it together. So here I'm using tangent, and then I put it on degree, so I know it's reading degrees. I put in 40, I close, and then on the right side, I have my answers. I have 0.839099632. Now, plugging that in might be a little cumbersome. So, there's 2 ways that we'll use, right? And not every answer is going to always be exactly the same, but I'm going to round this to 2 decimal places. And that's usually a good rule of thumb, to round to 2 decimal places when it comes to this. I'm plugging in a degree, I'm getting out a terminal point. And when I multiply these together, right, that's going to be 2 times 0.84, and that gives me 1.68. Oh, it actually gives me a fraction version, but this I'm okay with. I normally would prefer fractions, but since we're using a calculator already, I'll stick to 1.68 for my answer. And that's going to be here for angle B. I'll choose red. approximately 1.68 because I did approximate. Now, what I said before, I can just take the Pythagorean theorem and solve for this missing side. But like I said before, I don't want to use that method just because I want to practice using these trig ratios, more examples that I can give. Now, if you notice something, I now have angle B. So looking at this equation, this is no longer an unknown variable. So if you wanted to substitute 1.68 and then solve for that angle, you can. That would be, you would be able to do that. But just to show another example, let's say that you didn't think about this. I want to give you as many options as possible. So instead of using sine of A, I'm going to use, so I'm going to block this off. I'm going to use sine of 40 degrees, just like I used in tangent. Now for 40 degrees, we use opposite, which the opposite is the 1.68 over, and then hypotenuse, which our hypotenuse is C. And with a little bit of algebra and some cross multiplication, or multiply C to both sides, or let me just do that so no one gets confused. Let me move this a little bit. I'll bring the calculator once I need it again. So here I'm going to multiply C on both sides. Same thing I did with 2 on the previous example. That would leave me with C sine of 40 degrees is equal to 1.68. And then I'm going to divide by sine of 40. I'm just trying to solve for C. And I want you to remember, this is just the 40 is just the argument. This is just a word. So don't try to divide by 40 because that's, you can't have 40 degrees without sine. They go together. There's no way of splitting it up. Right? It's like saying, let's look at A and like, I'm going to just do the little tower and then the little dash in the middle. Like it goes together. Right? It makes no sense to separate them. And if you are, then you have a misunderstanding of this trig function. That ultimately leaves me with C is equal to 1.68 divided by sine of 40 degrees. Now, I'd urge you to be careful when you're using your calculator. That's why I try to avoid it as much as possible, because sometimes we tend to want to plug everything in one step. But the problem becomes our calculators use order of operations. Now, luckily the calculator I'm using naturally is, if you look here, it's naturally, when I put division, it naturally did this dividing symbol. Now, if I were to divide this way, you have to be careful if you write it in a straight line. Sometimes it works fine because there's no, obviously sine 40 degrees is not multiplication. But if you don't close your parentheses, you don't put parentheses, you might accidentally get the wrong answer. So just be careful, right? Try this same example on your calculator and make sure you're getting those same answers. So here I'm rounding again at two decimal places, but the decimal in the thousands place, that 3, is not going to change that 1. So it's going to be 2.61 is our hypotenuse. So that is equal to 2.61. And now for the last one, we have to find this angle, right? And that's where 6.4 comes into the picture. Because in 6.4, that's where you start trying to solve angles. 6.2, you're doing trig ratios to find the sides. But in 6.4, you are looking for the missing angle. Now, to find that missing angle, we do need to recall. So I'm going to recall those inverse properties that we discussed in the previous video, that you can apply the inverse through composition and it would simplify to the argument. Because, and let me use a different trig ratio for this next example. This next example I will use, let me block this off so we don't get mixed up. I'm going to use cosine of A, which cosine is adjacent over hypotenuse. Now before, this would have been a really bad choice, because before this would have been adjacent, which is B, over hypotenuse, and everything would have been missing. There would have been 3 unknown variables and only 1 equation. But now I know what the adjacent side is, 6.8. I know what the hypotenuse is, which is 2.61. And remember, some of our answers might vary slightly. So when you're checking your answer in the book, know that there might be some rounding error when it comes to these problems, just because, not error, but difference. There might be a rounding difference. Now, let's take our problem. And we have 1.68 divided by 2.61. And that is an approximation, of course. Cosine of A is approximately, and again, I'm around to 2 decimal places. And let's not forget, we already know what this angle should be. Oops. You have to be careful. If you notice, my answer changed because I accidentally put 2.6 pi. So you want to make sure you're careful when you're doing these, because that little bit you could look the wrong way and have a different answer. So I'm going to put 0.6. I'm around to 2 decimal places, which is going to be 0.64. And now the issue becomes, how do I isolate this argument? That's where we have to use our properties of inverses or properties of cancellation, whatever you see fit to call it. So to do that, now the inverse of cosine is going to be cosine inverse, and it's through composition. I'm not doing this through multiplication. This is not multiplication. This is me taking the entire function and plugging it in to this problem. Now what happens on this end, I'm choosing to believe all this exists. Everything is inside its domain and its range. And it definitely is true on this right hand side because 0.64 is definitely in the range, which means everything we're doing is sound. And that allows me to be left with the argument, right? If I make a quick note again, this right hand corner, I'm using the property of inverses that tells us that if I apply the composition, right, or let me write that a little differently because some of you might remember it as f of g of x, which means f inverse of f of x is equal to just the argument. Now that gives us cosine inverse of 0.64. And this is where I need to bring my calculator back in. And once again, make sure you're in degrees. I'm not looking for a radian. Remember, what goes inside of inverses is terminal points. What comes out of inverses is radians or degrees. But because this is a triangle, we're looking for an angle. So I'm looking for a degree here. So I have to go to my cosine inverse and plug in my 0.64. And we rounded the 1.68 divided by sine of 40, which I'll point to what I'm talking about. So we rounded this multiplication. Oh, sorry, it started all the way with we rounded tangent 40. We rounded the 2 times 0.64. That one gave us 1.68. And then we rounded again for 1.68 divided by sine of 40. Then we rounded again by dividing, right? We rounded the sine of 40. We're rounding the division. And then that we rounded that division to plug into our cosine inverse. And that's why we're getting 50.20815. Oh, sorry. 50.2081805, and that's the degrees. But I'm going to round this to my nearest degree. If you notice, if I round this to the nearest whole number, it's going to be 50. And that's exactly what we said angle A is supposed to be. Now, yes, we had a slightly different answer in our calculator, but it's because all these numbers, the tangent 40 is rounded. This multiplication, this number is the product of rounding tangent 40. We rounded sine 40, and then we divided those numbers. Hence, what we use is going to give us something slightly different. So it's something that we have to keep in mind. There's a lot of rounding that goes on here. And that is our complete circle. Now let me start another example, and then I'll have everyone else finish that example. I'll try to start it. And just to not make this video super long. But like I said, this is 6.2. This is 6.4. Oops. So here's the angle. Second example. Here's a triangle that we have. So we have the hypotenuse is missing. The two angles are missing. But we have that the triangle is 90. We have 2, and then we have 3. I'm going to do one quick example because I did 2 versions of using trig ratios, and that's how 6.2 is going to be. But let me do another version of doing this cancellation property or inverse property. So I'm going to try to use tangent of B. No, I'll do tangent of A. And that is opposite. It's going to be opposite of A is 3. Adjacent to A over adjacent, right? Because SOHCAHTOA is opposite over adjacent. So opposite is 3, adjacent is 2. And then I'm going to repeat the same process I did. I want to isolate. And again, one unknown, one equation. That's all I'm looking for. So I take tangent inverse on both sides. That gives me tangent A, and then 3 over 2. The cancellation property. Then I have A is equal to tangent inverse of 3 over 2. And this is going to be an approximation. Once again, I'm going to have the function is tangent inverse. The numbers are 3 over 2. Close my parentheses. And you can see there, I'm going to round this to the nearest degree. And that's going to give me 56 degrees. And that's angle A is 56. And try to see if you can continue using these trig ratios only, just for practice. Again, you can now use the sum of the interior angles, so on and so forth, but I only want to see trig ratios to find these missing sides. Same thing, I can use the Pythagorean theorem to help me find my hypotenuse, but I only want to use trig ratios to help me find these sides. So try finishing this triangle, and I'll give more examples for you to try.